In this lesson, we'll continue our discussion of the chemical level of organization by taking a look at something known as pH, acids, bases, and we'll finish up by looking at salts. So, in order to understand pH, we need to discuss hydrogen atoms. If you had your periodic table out and you looked, you would see hydrogen in that top left-hand corner. You see it has the atomic number of 1, which tells us that it has one proton. The number of electrons equal the proton, so that means it has 1 electrons, and its atomic mass is about 1, so that means it has no neutrons. One of the things about hydrogen is that it easily loses that electron. When it loses that electron, it becomes positively charged, and we call that a hydrogen ion. So this is the first time we're really seeing and working with hydrogen ions. One of the things about them is they are extremely reactive when in solution. If they became excessive, right? There's too many of them inside the cell or in a tissue, they actually can become harmful to that cell and the tissue. This is a little bit advanced, you don't have to know this, but there's actually a condition known as acidosis where we become too acidic. It could be fatal. Right? It could actually be fatal. So we're concerned with the amount of these hydrogen ions. We've got to always make sure there can't be too many of them. So pH is the concentration of these hydrogen ions in a solution, right? We want to be able to measure them. If we'll see in a moment, if they become too excessive, we become acidic, right? We become too acidic. So there's something known as a neutral pH. This is a state where, or a solution, let's say, that is neither acidic or acid, nor basic or a base. Right? There's an equal balance of hydrogen, which makes something acidic, and an OH, which makes something basic or alkaline. This OH group I have written for you here is known as a hydroxide ion. Right? It's known as a hydroxide ion. So a good example of a chemical that would be neutral would be pure water. Don't worry about the number 7 yet. We'll talk about that in a minute. But pure water has a equal number of hydrogen ions, which makes something acidic, as well as an equal number of hydroxide ions, which makes something alkaline. If these are equal, right, the solution is neither an acid or a base. Right, so pure water will dissociate into a hydrogen ion and a hydroxide ion. I drew it for you here, H2O. One hydrogen will be here, and then the other OH will be here. But like I said, these ionize. That hydrogen loses that electron, and it becomes this hydrogen ion, and then the OH has a negative charge. Since there's an equal amount of hydrogen, an equal amount of OH, pure water is at a scale of 7. We're going to see the pH scale is a scale of 0 to 14, where 7 is right in the middle, representing neutral. So what makes something acidic? Right? When something has an acidic pH on the pH scale, you're going to find it to the left. It's going to be lower than 7. And what's important is highlight right here. There is a high concentration of hydrogen. Right? As we have more and more hydrogen, the pH scale goes down. Right? So like a pH of 6.8 is a weak acid, but a pH of 1 we're going to see is a very strong acid. On the other side of 7 is the basic or alkaline pH. Here we're going to see low hydrogen concentrations, but highlight right here, high levels of hydroxide OH. Right? So the more OH we have, the more alkaline we're going to be. This number I want you to know. pH of human blood is on the alkaline side. It is 0.735. I'm sorry, 7.35, 7.35 to 7.45. All right, it's going to always we want to keep blood right in this range. Right, if blood became too acidic, like I said before, it could be fatal. So let's take a look at the pH scale now. Like I said before, it goes from 0 to 14. This scale has an inverse relationship with hydrogen concentration. What I mean is this: the more hydrogen ions, the lower the pH. Right? That's a stronger acid. The fewer hydrogen ions is going to mean a higher pH. Let's take a look. So here's a pH scale. So you'll notice it goes from 0 all the way up to 14. All right, so if you cut that in half, 14 in half is 7. So this would be neutral. An example of this would be pure water. So now as we go this way, we're going to get more and more. See how the arrow is going this way? More and more hydrogen ions. And this would be a strong acid. Over here is a weak acid. So they kind of drew this kind of like a lighter red or pink. And then here it gets darker, showing you that it's stronger. So it's just some example of things here that would be a weak acid: saliva, milk, right? As we go towards a pH of 4, tomatoes, grapes, 3, beer, vinegar, wine, pickles, that type of thing. They're going to be in this area here. And then a very strong acid would be hydrochloric acid. That would be in the stomach, right? If you poured hydrochloric acid on your skin, you would have a severe burn. The pH scale over here, from neutral this way, we're having an increased concentration of not hydrogen ions but hydroxyl, and that becomes more basic. So in the body, things that would be on the alkaline side would be blood. Notice urine can range from being acidic. Most of the time our urine is a pH of 6, because this is a way we get rid of excess hydrogen ions. It actually goes into our urine and we get rid of it. But urine could go all the way to alkaline. So it has a range. But most of the time, you guys will study this in A&P too, urine is about a pH of 6 on average. But it's a good way for us to get rid of hydrogen ions in the body. We'll eliminate them via the urine, right? That's why it's more acidic. Um, just some other things that maybe, we don't have it on here, but things that may be closer to 8 would be like bile. That's kind of an alkaline, or pancreatic secretions. Those are going to be in the alkaline region. But just other things that are not in the body that are alkaline: eggs, ocean water, household bleach, ammonia. You'll see a lot of industrial cleaners are going to be in the alkaline, right? Strong alkalines. Oven cleaner, right? Extremely strong alkaline. Okay, so it's important to know that neutral is 7. As we go from 7 towards 0, that acids are going to become stronger and stronger. On this side, we have no hydrogen ions, but more hydroxyl. Right, and again, I do want you to know the pH of blood: 7.35 to 7.45. Okay, so what is an acid? We kind of went over this already. An acid is a chemical that's going to add hydrogen to a solution. An example would be stomach acid, right? If you it's called HCl. If you took hydrochloric acid and you dissociated, you would get a lot of hydrogen ions plus chloride. Um, a strong acid means that let's say the hydrochloric acid would completely dissociate, where we would have a lot of hydrogen ions in solution. Don't write this down, but a weak acid would only partially dissociate, so we wouldn't have as many hydrogen ions. A base is a solution that, watch this, removes hydrogen ions from a solution. So these are going to take hydrogen ions out, and we're going to tend to see more OH. And then finally, guys, weak acids and bases. I kind of mentioned this before. A weak acid fails to completely dissociate. We actually use these weak acids and base to act as buffer systems, which help to balance the pH. Again, buffer systems is a little bit beyond the scope of this course. That's something that's covered more in detail in A&P2. We'll talk a little bit about it on our last slide. Finally, a salt. This is a solution that dissociates into a positively charged ion, but not hydrogen ions, and also a negatively charged ion. Okay, that is not an OH, because again, if the hydrogen ions made something an acid, the OH made something a base. So in this case, the positively charged ion would be, say, let's say sodium chloride. Sodium would be the positively charged ion, and then chloride would be the negatively charged ion. That would be classified as a salt. Again, an acid is going to produce hydrogen ions. A base is going to produce OH ions. Salts, they have cations and anions, right? Positive and negatively charged ions. However, they're not hydrogen ions or hydroxide. There's something else. All right, so if you want to put down as an example, sodium chloride, NaCl, will dissociate into Na positive and Cl negative. Okay, just to finish up acids, bases, and salts, we do have buffers, right? Well, what I want you to know right now is that buffers help to stabilize the pH of solutions, right? We don't want to become too acidic. We don't want to become too alkaline. Right? Buffer systems often involve a weak acid and its related salt, which is a weak base. They function, here's the important thing, they function to neutralize strong acids or strong bases. One of the ones that you're going to study in A&P2 is known as the carbonic acid bicarbonate buffer system. Right? That's one of many, and it's important to our survival. This takes place in our blood. Sometimes you may have dealt with acid base before. Sometimes when people have too acidic stomach, right, too much acid in their stomach, they'll take like a Tums or a Rolaids, and that is acting as a buffer to neutralize the stomach acid, right, to help get rid of too much stomach acid. All right, so again, for our purposes this semester, this is a little bit advanced. Just know that buffers help to control or neutralize strong acids. And then we also have buffers to neutralize a strong base. But in the body, we worry about us becoming too acidic. Okay, so that concludes this lesson on pH and acids, salts, and bases.